All right, so when we go back and look at the problem-solving techniques that we used so far, what were they? How many different problem-solving techniques did we use? 3? Well, what were those 3? Yeah. Dimensional analysis is probably the biggest, and then algebra, and what was the last one? Multiple equations. Right? And so those are pretty much the 3. So the question might come up, like, for example, dimensional analysis versus algebra. Here I have degrees Fahrenheit is equal to degrees C plus 32 degrees, a 9/5 degrees C. And the question comes up is, why can't we do this conversion using dimensional analysis? So I know the conversion factor. The conversion factor is like this. If I want degrees Fahrenheit, then the relationship between Fahrenheit and Celsius is given by this. There are 180 degrees Fahrenheit for every 100 degrees Celsius. And so, excuse me, what we see here is something like this. Like if I start off at 0 degrees Celsius and go up 100 degrees here, then that would be equivalent to starting off at 32 degrees Fahrenheit and then going up to 212 degrees Fahrenheit. And so here I'm going to have 100, steps up. In other words, 100 degrees. Over here, how many degrees or steps are there on this scale? And so going from 32 to 212, that would be 180 degrees, correct? Yeah. And so the conversion factor should be something like this. If I have my degrees C, then I should be able to get my degrees Fahrenheit just by using this relationship, this proportionality between Fahrenheit and Celsius, right? And you'd say, no, because that's not the equation, but why not? Why doesn't that work? Because is this true? Is this true? Let's say, in other words, every degree C is about 1.8, in fact, not about, it is 1.8 degrees Fahrenheit. So for every degree C that I go up, I need to go up by 1.8 degrees Fahrenheit. Is that always true? Or in other words, for every 5 degrees C, I need to go up 9 degrees Fahrenheit. Is that true? And so we could look at a thermometer and then take a look and see if that seems to be the case here. Let's see if I have it. This isn't the most precise thermometer here. Oops. Actually, you can't see it. So starting off at 0, going up to 100, so we have 100. Starting at 32 to 212 is 180. And the conversion factor is 180 to 100. And the problem with this is it doesn't work. Why doesn't it work?
The zeros aren't the same.
Yeah, exactly. It's because the zeros are offset. Do you see this 0 and this 0 are offset by how many degrees? This 0 and this 0 are offset by how many degrees? 32 in the Fahrenheit. Since they're offset, we can't do this using the straight dimensional analysis. We have to add this factor here. the 32 degrees to compensate for the mismatch in how the scale started. In other words, if this were true, the zeros would have to match, such that it at 0 degrees C, it'd be 0 times 180, which is 0, divided by 100, which is 0. And so 0 degrees C would be 0 degrees Fahrenheit. Then it would work, if the zeros match. Now, in this case, we have to use algebra. We can't use dimensional analysis. However, in our Chem 4 book, we have another problem. In our Chem 4 book, we're not looking at the temperature, we're looking at something else. We're looking at delta T. Delta T. And so when we're looking at delta T, that's a little bit different. Delta T just means the change in temperature. And so let's say I have a temperature of 75 degrees. What should I do? 75 degrees Fahrenheit, dropping down to a temperature of 25 degrees Fahrenheit. And I look at the temperature drop, that's called a delta T. Now, what is the temperature drop here? Would it be 50? Yeah, it would be a 50-degree temperature drop. But if somebody said the change in temperature was 50 degrees, if they just said it was 50 degrees, would you know if it was an increase or a decrease in temperature? You wouldn't know, and so we lose that. That's called phase information. So what we say is delta T is equal to minus 50 degrees Fahrenheit, so we don't lose that information. It's a temperature drop going from higher to lower. This is why we use the equation T final minus T initial. Do we take the absolute value of that? No, it's just T initial minus T final. In fact, we rarely do absolute values. In this class, we're never going to do anything with an absolute value. So we're kind of, in other words, we need to know what that is. Is it negative or is it positive? Because if it's negative, that means the temperature dropped. If it's positive, that means the temperature increased. We'd be at 125 degrees. That's important in science. Sometimes you don't know. So, for example, what is the square root of 4? What is the square root of 4? It's plus or minus 2. Well, which one is it? Is it plus 2 or minus 2? You can't tell, can you? You can't tell because you just lost that information. So in science, we keep track of this thing. If it was negative 2, then we do that. If it's negative 2 squared, and that gives us 4, then we represent that different than 2 squared, which is equal to 4, even though these two things are the same. And so in our book, we color-code it. Like one's color-coded red, the other's color-coded blue, so we know which one came from which. Because in science, we deal with waves. And in waves, it makes a difference if it's positive amplitude versus if it's negative amplitude. Have you heard of like noise canceling headphones and that kind of stuff? How do noise canceling headphones work? Do you know how they work? They take a positive wave and then combine it with a negative wave, and when you take a positive wave and a negative wave, what happens? They cancel each other out, and there's no more amplitude. However, if you take a positive wave and the positive wave, what's going to happen? Those build up in amplitude. Or negative wave and a negative wave, those build up. And so this type of information is important for us. This is called phase information. This phase information is important for us because we deal with waves, and with waves we need to know, are we at the peak or are we at the valley? If you take the absolute value, then you've just lost that information. But this is an aside, you don't have to worry about that. So this is why it's important for us to know it's negative because it's dropping. Does that mean the temperature is negative 50 degrees Fahrenheit? If the temperature drop is negative 50 degrees Fahrenheit, is the room at negative 50 degrees? I mean, the room could be at 100 degrees Fahrenheit. But if there was a minus 50 degree temperature change, then it must have started at 150, right? And so delta T is different than the T. For delta T's here, we have two ways we could solve this. One way we could solve this is just using dimensional analysis. if we use dimensional analysis, then this works. It's a minus 50 degree Fahrenheit change. And then we know that for every 180 degrees Fahrenheit, this is dimensional analysis, we want to cancel out the degrees Fahrenheit. For every 180 degrees Fahrenheit, we have 100 degrees Celsius. And so what would the change here be? The change here would be 50 times 100 divided by 180. 27.7. 27. Actually, I'm only allowed 2 sig, or 1 sig fig. I'll just carry it to 2 sig fig. 27.77 degrees C. Or, if I did this algebraically, it would be minus 50 degrees Fahrenheit times 100 degrees C over 180 degrees Fahrenheit. Actually, this is, no. If I did this algebraically, I need to solve this equation for degrees Celsius. And so this would be degrees C is equal to degrees Fahrenheit minus 32 degrees times 5/9 or times 100 over 180. That would be it. And so it would be minus 50 degrees Fahrenheit minus 32 degrees Fahrenheit times 5/9. So that would be that equation there. So let's do that. So 50 times 5 divided by 9 minus 45.5 degrees C. And so which one's correct? A 50 degree drop here corresponds to a 27.7 degree drop if we do it using dimensional analysis, or a 45.55 degree drop if we use the algebraic equation. All I did was I took this equation and rearranged it. Degrees Fahrenheit is equal to 180 over 100 degrees C plus 32 degrees, and then solve for C, and then plug that here. And so which one do you think it is?
Dimensional analysis.
It's the dimensional analysis. In fact, this is wrong. We have to use dimensional analysis when we're doing a delta t. Why? Because the starting point we could always just say is 0, you know, same starting point. And so the starting point, if we just say it's 0, then we start off at 0 and drop 50. If we start out at 0 and drop 50, then we start at 0 C and drop how much in degrees C? Well, the temperature drop is going to be the same, but the step, the size of the step is different. And so that's the delta T. Now we could use the equation like this. Alternatively, we could solve it like this. We could go 75 degrees Fahrenheit. Well, 75 degrees Fahrenheit and degrees C is this. Degrees C is equal to 75 degrees minus 32 degrees times 5/9. 5/9 is 100 over 180. And so let's try that. 75 minus 32 equals times 5 divided by 9. And so it's 23.88 degrees C. Or actually, I'm only not allowed that many sig figs. Let's just go with 23.8. I should try to keep consistent with my sig figs. And then 25 degrees Fahrenheit would equal what? Well, the degrees C is equal to 25 minus 32 times 5/9 degrees. And so that's going to be minus 7. Times 5 divided by 9. Minus 3.8. So minus 3 point, actually I'm allowed 2 sig figs, it looks like, so 3.8, so 8 degrees C. So what's the temperature change here? What's our delta T? Our delta T is, so our initial temperature is 23.8 degrees Celsius. Our final temperature is 3.88, minus 3.88 degrees Celsius. And so our delta T is going to be 27 point. All right, so I could do it algebraically. I'd have to do it by figuring out the initial temperature algebraically, figuring out the final temperature algebraically in degrees Celsius, and then subtracting the two. Or I could do a dimensional analysis just by taking the delta T. The delta T doesn't matter where the zero is, and then doing it that way. And they should come out to the same answer, but did they come out to the same answer? No. They're a little bit different. So is there a mistake? It turns out there's no mistake. There's no mistake. If there's no mistake, why are the answers different? There's no mistake, but the answers are different because of rounding error. Which one of these answers do you think is better? The dimensional analysis? Yeah. This is better. This is a better answer because I didn't carry all the digits in my calculator. I just carried one extra digit. Do you see that? Here. If I carried all the digits in my calculator, then the two answers would come out the same, or awfully close to the same. So let's go ahead and redo this. This answer is a little bit better because what I did was I wrote down 23.8, but what the calculator had is a little bit different. And so what the calculator had is this. I'll have to recalculate it. So it's 75 minus 32 equals times 5 divided by 9. Times 5 divided by 9, 23.8. I'm going to write down all the digits in the calculator. So 3, 6, 7 eighths. 1, 2, 3, 4, 5, 6, 7 eighths, and then a 9. And so that probably is from the calculator rounding it off. And so that's my initial temperature. My final temperature at 25 degrees C would be 25 minus 32 equals times 5 divided by 9. And that's minus, my final temperature is minus 3.88. And here I'm going to have 8 eighths. So that's 4, 5, 6, 7, 8 eighths, and then a 9 degrees C. And then subtract the 2. So this is going to be 23.88888889. And the delta T here is minus 27.77, you see, etc. And so I get the exact same answer if I carry all the digits in my calculator. So this is called round off error. The more calculations you do in order to get the answer, the more prone you are to round off error, because sometimes we'll just round it rather than carry all the digits in the calculator. Here, there's only one operation, essentially one step, so it doesn't suffer from round off error as much as the other one. All right, so we have dimensional analysis and algebra. And so what you take a look at is, when do you use dimensional analysis and when do you use algebra? This is not so easy. So for temperature, you might not ever use dimensional analysis. You can always use the algebra method that we did in the second one, but it just takes more time. So when we get to number 76 here, let's take a look at how we can do that. So Fahrenheit and Celsius thermometer are immersed in the same medium. At what Celsius temperature will the numerical reading on the Fahrenheit temperature thermometer be 49 degrees less than that on the Celsius? And so what we want is degrees Fahrenheit is equal to degrees Celsius minus 49 degrees. And so the Fahrenheit reading will be 49 degrees less than the Celsius reading. At what temperature is this? Well, it certainly isn't 0 degrees C. Because at 0 degrees C, what is the Fahrenheit? Well, it's 32. So that's not right there. So we gotta figure it out. And so we don't know both. We don't know the degrees Fahrenheit, nor do we know the degrees Celsius. And so that's a two unknown problem. A two unknown problem requires two equations. So this is equation 1. What's equation 2 for this problem? Well, equation 2 is this. We know that degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32. And then when you have two equations and two unknowns, you just do a substitution. So what we'll do is we'll just substitute this in here. If we do that, then let's simplify. We're going to get degrees Celsius minus 49 degrees is equal to 9/5 degrees Celsius plus 32 degrees. And so we'll combine terms here. I think the easiest is to subtract 32 from both sides. So if I subtract 32, I'm going to get 81 minus 81 degrees is equal to, now I'm going to subtract, well, 1 degree C is the same as 5/5. So 9/5 minus 5/5 leaves me with 4/5 degrees C. And therefore the degrees C is equal to 5/4 times 81. Be negative. So I'll just do that on the calculator here. 5 times 81 divided by 4 comes out to 101.25. All right, so if I'm at 101.25 degrees C, then the Fahrenheit should be 49 less than that. And so what's 49? So I'll just take that. So the Fahrenheit should be 49 less. So 101.25 minus 49. 52.25. So the degrees Fahrenheit should be 52.25 degrees. And so I have my degrees Celsius here, and my degrees Fahrenheit here. Is there a way to check my answer? There is a check. I can check my answer. These two temperatures should be the same. 101.25 degrees C should be the exact same temperature as 52.25, and the Fahrenheit temperature should be 49 less than the Celsius temperature. And so let's check this. The way I'm going to check this is I'm just going to check one of these. So I can check either one. Let's check degrees Fahrenheit. Degrees Fahrenheit should equal 9/5 degrees C, which would be 101.25 plus 32. And so if they're the same temperature, then I should get 52.25. And so this is just a quick check to see. Or I could do a mental check. If I do a mental check, then you have to have some numbers memorized. For example, what's the boiling point of water in degrees C? 100. And so this is about 1 degree warmer than the boiling point of water. And then does this look right to you? 52.25 degrees Fahrenheit is like a little warmer than boiling water. Does that look right to you? No, that doesn't sound right. I mean, 52.5 degrees Fahrenheit is an awfully cold day. Water is not going to be boiling there. It doesn't make sense. So I made a mistake. I must have made a mistake because it's impossible.
The value of the degrees Celsius vectors is multiplied by.
Oh, yeah. Here's my mistake. Do you see it? This is not supposed to be positive 101.2, but it's supposed to be negative because I didn't carry the sign through. And so this should have been negative 101.25. And this is not going to work. It can't work because 52.25 degrees Fahrenheit is nowhere near boiling water. And so let's redo that. Well, if it's 49 degrees less, then it's going to be minus 101.25 minus 49, which is going to give me minus 150.25 degrees Celsius. And so the Fahrenheit temperature must be 49 less than the Celsius, and it's got to be 101.25 for the Celsius and 150.25 negative for the Fahrenheit. And these two temperatures must be exactly the same. And so let's check this one here. And so the check is going to be, let's see if the degrees Fahrenheit is minus 150.2 when the degrees Celsius is that. And so what we'll do is we'll do the same thing. It's going to be 9/5 times the degrees Celsius minus 101.25 plus 32. And so 9 times 101.25 negative divided by 5 equals plus 32. Oops. (150.25). Negative 150.25. So that checks out. Both temperatures are the same, and we meet that secondary constraint. And so we could have seen that here if our thermometers went down far enough. Let's take a look. Do our thermometers go down that low? Because eventually, once we hit minus 101.25 down here, then the Fahrenheit should be at minus 150.25, but our thermometers aren't doing that. Well, you could buy longer or bigger thermometers, but there's no use in doing that because we can just calculate it on the break. Okay, let's try one more. Okay, what Fahrenheit temperature will the Celsius temperature be twice? Or that is Celsius. In other words, the Fahrenheit thermometer will read 2 times what the Celsius thermometer is reading. And so to do this one, we set up one equation. What's the equation we'll set up based on that sentence there? The Fahrenheit thermometer will be twice the Celsius thermometer reading.
Fahrenheit equal to 2 times degrees Celsius.
Yeah, 2 times degrees Celsius. And so that's one equation. What's the other equation?
Degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32.
Yeah. And then we just do a substitution. We'll substitute that in there. So we'll get 2 times the degrees Celsius is equal to 9/5 degrees Celsius plus 32 degrees. And then what I think I'll do is I'll subtract 9/5 from both sides. So 2 will be, 2 is going to be, how many fifths? 10/5. 10/5 minus 9/5 gives me 1/5. So I'll have 1/5 degrees C on the left is equal to 32 degrees. And so my degrees Celsius is equal to 5 times 32, 160 degrees Celsius. So if I'm at 160 degrees Celsius, then the degrees Fahrenheit must be double it. And so the degrees Fahrenheit should be 2 times that, which would be 320 degrees Fahrenheit. And then let's check our answer. The check here is we'll just recalculate the degrees Fahrenheit based on this degrees C. And so degrees Fahrenheit is equal to 9/5 times 160 degrees C, or actually I don't want C there. Because, you know, I'm not using, I should be using dimensional analysis proper, but I'm not using it to make the equation easier to remember. And the dimensional analysis is, this is 9 degrees Fahrenheit for every 5 degrees Celsius. That's the equation. And then things would cancel out properly here. And then this is going to be plus 32 degrees here. So when I do this and plug it into the calculator, it checks out. 160 degrees Celsius is indeed 320 degrees Fahrenheit. Well, if 160 degrees Celsius is 320 degrees Fahrenheit, then what would 161 degrees Celsius be? Would 161 degrees Celsius be 322 degrees Fahrenheit? Would that be true or false? That'd be false. I mean, it just only happens at this one point where they coincide, like this. It's just because the scales are offset. All right, so C and D are the same, you know, kind of problem. Multiple equations, multiple unknown type problem. Okay, are there any questions on this? No questions? Because what I'd like to do is I'd like to move on to the next chapter, chapter 4. So leave this chapter 3, move on to chapter 4. We can come back to chapter 3 anytime. But let's take a look at chapter 4. Chapter 4 is Introduction to Gases. We will be using dimensional analysis in chapter 4. But let's take a look at the learning objectives. The learning objectives are macroscopic. We've described 5 macroscopic characteristics of gas phase matter. Then we use condensed molecular theory to explain these characteristics here. You know, theory does what? Theory offers a very fundamental description of the phenomena. The phenomena would be described. We already talked about this, actually. This is kind of review. Define pressure and imperfect statements in which the term pressure is used. Explain the cause of the pressure of the gas. We'll be talking about pressure, gas pressures. Am I missing something? I seem to be ahead quite a bit. Did we do the seawater problem?
Yeah.
Sodium chloride? Okay. Oh, shoot. I know what. I skipped something. I'm sorry. I skipped something. So this was the 2 equation 2 unknown. Type of problem here. And so we have 3 problem solving methods: dimensional analysis, algebra, two equations, two unknowns, or multiple unknowns, multiple equations, or system of equations. But when we look at dimensional analysis, there are going to be some variations to dimensional analysis. Let's take a look at one variation, which is quite common. Normally, what we try to do is we try to cancel things out, using the denominator. What we're trying to cancel out is in the numerator. But sometimes we try to cancel out what's in the denominator. And that means we have to invert the conversion factors. So let's say I have water. What's the density of water? 1 gram. Can we be more precise than that, or we can't be? So 1 gram per milliliter means that water varies anywhere from 0.5 to 1.4. Can we be more precise than that or not? Yeah, I would say 1.0. Can we be more precise than that? Not really. I mean, we might go 1.00, but that would narrow down the temperature range. So we'll just go at 1.0 grams per milliliter. That's the density of water. So sometimes in dimensional analysis, we don't start with a single number in a single unit. We might start off with a ratio like this, proportionality, the density. And so rather than, most of the time, this is our conversion factor. How many times did we use this as a conversion factor already, the density of water? Actually, a number of times. But in this case, this is our given. Because what we want to do is we want to figure out the density of water in pounds per gallon. You might have that number memorized. Do you have it memorized? How many pounds per gallon is there? We had to learn this. We had to learn this in the, you know where I learned this? The first time I memorized this was I was in the Boy Scouts for a while, and then, we would go on a backpacking trip, and so we had to calculate, because there wasn't enough. The first water was going to be like 8 miles in or 10 miles in, I forgot and then there was no water up until then, so we had to calculate, well, we need to carry water. Well, how much water are you going to carry? So I memorized, water is 8 pounds per gallon. I memorized that, forgot, years ago, 8 pounds per gallon. Well, let's go ahead and calculate. We can calculate it. If you ever forget, you can use dimensional analysis to calculate it, because we know water density is 1.0 grams per milliliter. And then this is a variation of dimensional analysis, because we need to convert the numerator to pounds, and we need to convert the denominator from milliliters to gallons. Doing the top is just our standard. Our standard is we need to get rid of grams. What can we use to get rid of grams here? What can you relate grams to? To pounds? Yeah, actually we can relate grams to pounds straight, because, and this will be given. Because it's not exact. 1 pound is equivalent to 453.6 grams. So it's not exact, let's just use it. So 1 pound is 453.6 grams. And therefore the grams cancel, and that leaves us with pounds. Well, that's what we want, pounds. So this is what we call one-step dimensional analysis problem. But it's more complicated, because we're done with the numerator. We still have to tackle the denominator. And so the denominator, we got to go from milliliters. But now, instead of canceling it out down here, we got to cancel it out up here. And so the milliliters will cancel the milliliters. Milliliters in the denominator cancel. And so this is the variation that I was talking about. So we don't always cancel it in this way. Sometimes we have to cancel it in the opposite way. But what can we relate milliliters to? Liters. So there are 1,000 milliliters to a liter. Everyone should know that. 1,000 milliliters to a liter. And so the milliliters cancel, and that leaves us with liters on the bottom. And then where? Well, you're also going to be given that 1 gallon is 3.785 liters. So this is going to be 3.785 liters per gallon. And the liters cancel, and that leaves us with gallons. So our units work out. This is going to be pounds per gallon. So I'm going to calculate it out. Actually, I'll just use this calculator here. 1,000 times 3.785 divided by 453.6 comes out to 8.34 pounds. 8.34 pounds. Now, this is where round-off error comes into play. Let's say there were 100 Boy Scouts. Each Boy Scout is bringing 1 gallon of water. And you need to know the weight because maybe you're gonna fly there to the trailhead. And so we gotta make sure we calculate the correct amount of fuel for the plane. Are you gonna calculate the total weight by using 8 pounds per gallon? Or would it be more accurate to calculate 8.3? In other words, does this 0.3 or a third of a gallon make any difference? I mean, a third of a pound, not a third of a gallon. Does it make any difference? Yeah. Well, maybe for 1 gallon, not that big of a deal, it's 8 pounds. But if you're talking about 100 gallons, then is 8 pounds per gallon really precise enough? No. We probably want a little bit more because we have 2 ways of doing it. You know, the same thing with this 4, you know. I learned 8, but if it's 8 and a third, it's quite a bit different than just 8. And a third of a pound can add up if you got 100. That'd be another 33 pounds or so. And so we got to worry about round-off error, but we usually solve that problem by just carrying 1 extra digit. By carrying 1 extra digit than you're allowed in your intermediate calculations, you're really going to minimize the round-off error, and you don't really have to worry about it. But if you like to round every answer, then you got to worry about it because at the end, those third of a pounds will add up that you're rounding off. All right, so this is another variation. So 8.34 pounds per gallon of water. Okay, we're going to do one more variation here. Which is going to be number 75. In the United States, the volume of irrigation water is usually expressed in acre feet. 1 acre foot is a volume of water sufficient to cover 1 acre of land to a depth of 1 foot. And so here we have a composite unit. A composite unit being an acre and a foot. An acre is an area like this. So let's say this is an acre of land. And so this is an area. And a foot, if we submerge this acre in 1 foot of water, so it's 1 foot deep, then this would be the height. And so area times height is equal to volume. But this is a composite because the area is not in your ordinary units, but it's no big deal because we use dimensional analysis in exactly the same way for things like this. And so they tell us 640 acres is equivalent to 1 square mile. And 1 mile is equal to 5,280 feet. And so this one you may or may not have memorized, but this is exact. How about this one? Is this one exact? What do you think? Or approximate? How many sig figs do you think are in 640 acres? Infinite. It's most likely exact. You know, so if you're to buy 1 square mile, there better be 640 acres. There shouldn't be 635 acres. Somebody might say, oh, 635 acres is close enough. Right? I don't think so. I think it's gotta be exact because, you know, you don't wanna lose 5 acres right off the bat. And so most likely that's exact by definition. The principal lake in the California Water Project is Lake Oroville, whose water storage capacity is listed as 3.54 times 10 to the 6 acre feet. Express the volume of Lake Oroville in cubic feet. And so we have 3.54 times 10 to the 6 acre feet. .54 times 10 to the 6 acre feet of water. And so if somebody asks you, what is the strategy in dimensional analysis? What do? You know, some people will say, oh, it's easy. You do step one. Step one, do a gram to, and this is later on. We have something called the mole. Do a gram to mole conversion. Step two, do mole to gram conversion. That's easy. That's dimensional analysis. But no, that's too restrictive. That's like calling everything a molecule. Or everything black and white. No, there's going to be some variation here. And so what is the strategy in dimensional analysis? What should I do? Should I have it mapped out? Do you know where you're going to go from here? We're going to go from acre feet to what? Do you have any idea? No, you don't have to have any idea of where you're going to go. All you do is you look for something that'll cancel out. Ideally, we'd like something that cancels out the whole thing. So if we can convert acre feet of water to something else, then maybe we're there. Do you know of something that converts acre feet of water to something else? No. And so we start to slim it down. Maybe let's get rid of the water. If we get rid of the water, is there something that converts acre feet to something else? No. And then we go to feet. But if we go to feet, we have to be careful because what are we after? We're after answer A. Answer A is cubic feet. And so we could go from feet to inches. We ignore the acre and we convert just the foot. If we convert the foot to inches, this would be linear. If we convert the foot to inches, are we getting closer or are we getting farther from feet? Or if we convert the feet into miles, I could convert the feet into miles. Are we getting closer or farther? Closer or farther? Farther. In fact, I don't want to touch this because I have feet here, I need feet there. What I need to do is not change the feet. I need to change the acres. So is there something that gets rid of acres? Oh, sorry, over here. Is there something that will cancel out acres, convert it to something else? What is it? Yeah, in fact, by definition, there's 640 acres in every square mile. And so all I'm doing is canceling out just the acre part of the unit, but I'm leaving the feet. And so now I have a composite unit. It's going to be square miles for the area and feet for the height. And so I look, do I have a conversion factor that gets rid of square miles? Do I have a conversion factor that gets rid of square miles? Do you know what 1 square mile is equal to? No. And so let's not do the square. Do I have a conversion factor that gets rid of miles? Yeah, I do. What is it? Well, 1 mile is 5,280 feet. But this is miles squared, that's miles. And so I'm only going to be able to cancel out one of these. How can I cancel out both of these? If I square the whole thing, then I can cancel out both of these. So miles squared cancels out with miles squared. And that leaves me with feet squared. Well, a foot times a foot squared is equal to a foot cubed. And so I'm done here. I didn't really have a strategy. Well, I did have a strategy. The strategy is always the same. In dimensional analysis, you try to tack on conversion factors to cancel out the units. Change them to something else. Eventually you'll get there. And so let's go 3.54 times 10 to the 6 divided by 640 times 5280, and I have a square key on this. Works out. And so this is equal to 1.542 times 10 to the 11 cubic feet. So in terms of cubic feet, I could do this. I could move the decimal place, so this would be 10 to the 10, 10 to the 9. So this would be 154.2 times 10 to the 9 cubic feet. You know what 10 to the 9 is? 10 to the 9 is either, we have two words for 10 to the 9. One word is giga, right? Giga is 10 to the 9, is that right? And so this would be giga cubic feet. 154 giga cubic feet. Or there's another name for 10 to the 9. What is it? Not nano. Billion. And so giga is not used often for UCSC numbers, so we'll call it 154.2 billion cubic feet. It's a lot of cubic feet of water. Or we could go the opposite way. If we go the opposite way, we could do 0.1542 times 10 to the 12. What's 10 to the 12? Tera. So we could say that there's 0.1542 tera cubic feet of water. Or we could say trillion. And so this is equal to 0.1542 trillion cubic feet. Of water. And so those are some variations of dimensional analysis that you might run across here. All right, let's take a look at B. Can you go to cubic meters? Is that difficult? What would you do here? You go from cubic feet to, tell me the steps in going to cubic meters. So if we end up, let's say we're here at cubic feet, and then we go from cubic feet to, well, feet to centimeters. How many centimeters is in a foot? Can you tell me? No. We would go from cubic feet to cubic inches, and then from cubic inches to cubic centimeters, and then cubic centimeters to, and that would be the path. And then the path, how would we get to gallons? I would probably go from, to get to gallons, I'd probably go from cubic feet to cubic inches, from cubic inches to cubic centimeters to milliliters to, and then liters to gallons, and then we'd be there. And so all B and C just means just tacking on some more conversion factors or starting to take a different branch or something. All right, yeah, that's so I forgot to talk about some variations in dimensional analysis here. But let me go back to chapter 4. We're just looking at the learning objectives here. I just want to go through the learning objectives here, and then we'll take a break. All right, we measure gas pressure using different units: atmosphere, torr, millimeters of mercury, inches of mercury, pascals, kilopascals, bars, pounds per square inch. Pounds per square inch is probably the most common. Do you know what the air pressure in this room is in PSI, pounds per square inch? Roughly? It's about 15 pounds per square inch, the air pressure in this room. Describe the operation. There are two ways of measuring pressures. We could use a manometer or we could use a barometer for measuring pressure. So we talk about manometer, barometers. We'll talk about gauge pressure and atmospheric or absolute pressure. So gauge pressure versus absolute pressure. We'll learn about converting from one unit to another unit. These are too long. I just wish they'd just have the key words in the learning objectives. And then this. Learning objective 4.4. When plotting the relationship between gas volume and temperature, explain how the straight line can be extrapolated to determine the temperature at which the gas has zero volume and explain the significance of this temperature. Describe the relationship between the volume and temperature of a fixed amount of gas at a constant pressure and express that relationship as proportionality, inequality, and a graph. Given the initial volume, and okay, so when we look at this, do you know what they're saying here? What they're saying is this. What do we do with the scientific method? We start off with the hypothesis, we start off with the law, or we start off with theory, observations. So we take our observations, and then we come up. Oh, my battery's about to die. Can I bring my charger? Okay, let me